Hello, everyone. My name is Tim Ballard. I'm at the University of Queensland in Brisbane, Australia. And this is a project that I'm working on with Andrew Neal, Simon Farrell, and Andrew Heathcote. Our working title for this project is A General Architecture for Modeling the Dynamics of Goal-Directed Motivation and Decision-Making. This is a very broad title, so I want to start off by narrowing the scope a little bit and defining some terms. But before I do, I'll just point out that I put a link to the preprint of the paper on the slides, so anyone who wants to can read more about the project. The key construct that we're interested in here, of course, is goals. There are, of course, a lot of different types of goals. For example, a day trader might aim to hit a profit target by the end of the day. A bush firefighting team might have the goal of slowing the progress of a bushfire to a certain rate. Or we might have more abstract goals like being a better person. Here, we're specifically concerned with so-called SMART goals. So these are goals that are specific, they're measurable, meaning that progress towards the goal can be quantified, they're achievable, they're relevant, and they're time-bound, meaning that they have a deadline. For our purposes, the measurable and the time-bound properties are going to be the most important because these are the ones that are dynamic. By dynamic, I mean that these properties change over time as one pursues a goal. So you can think about the current state with regard to a goal as a position on this two-dimensional plane. So here, the x-axis represents what you might call the distance to the goal. So the distance is how much progress needs to be made in order to reach the target. So for example, if I'm hoping to raise $1,000 by the end of the month for charity, and I've currently raised 300, then my distance is 700. The y-axis represents the time to the deadline. So how much time remains before I'm expected to have reached my target. And the combination of these two dimensions determines the difficulty of the goal. So anywhere above this diagonal in the red region, it's a little bit easier to achieve because there's less distance to cover and there's less time remaining. Below the diagonal in the blue region, the goal is harder to achieve. The question we're interested in here is how does motivational value of the goal change as people move through this space? There's a great deal of theory that speaks to this question, but the theory tends to be, first of all, verbal, and second of all, is rather narrow in focus. For example, there's a whole class of theories that makes predictions about the relationship between the distance to the goal and motivation, which in this project we refer to as the distance gradient. But these theories generally tend to ignore the influence of time. And not only that, they disagree on the nature of this distance gradient. So there's what I've called the proximity perspective, which is shown in this left space here, which assumes that motivation increases as you get closer to achieving your goal or to reaching your target. And this perspective dates back to the goal gradient hypothesis. But there's also what I've called the discrepancy perspective, which assumes that motivation results from there being a discrepancy between your current state and your desired state. And as such, motivation decreases as you get closer to the goal, as you're rectifying that discrepancy. Here we modeled the distance gradient as a power function so that we can capture any diminishing returns in the relationship. So a positive exponent, a delta, gives you a positive distance gradient, which is consistent with the discrepancy perspective. A negative delta gives you a negative distance gradient, which is as assumed by the proximity perspective. There's also a group of theories, mainly based on models of temporal discounting, that address the influence of time. There's more agreement among these theories. The consensus is that motivation increases as the deadline looms. But these theories rarely take into account distance. They don't take into account how much progress needs to be made. So they ignore this distance gradient. Here we model the distance gradient in the same way as, we model the time gradient in the same way as the distance gradient. Except here we really don't expect the exponent to be positive here. So in the analysis I'm about to present, we're going to constrain tau to be negative. And then there's a third class of theory that doesn't explicitly address distance or time, but addresses the more general relationship between goal difficulty and motivation. And we call this the rate of progress gradient because difficulty is determined by the rate of progress that needs to be sustained in order to achieve the goal. So in other words, the ratio of the distance to be completed to the time available. Here there's also a conflict. So on the one hand, you have what you might call the expectancy perspective. This is largely based on expected utility models of motivation that assumes that motivation increases with the likelihood of achieving the goal. You're more motivated to pursue goals that you think are going to be easily achieved. And therefore, motivation reduces with the rate of progress that must be achieved. And so this is shown on the left here. There's the difficulty perspective, which is in the middle, which assumes that motivation increases with the rate of progress needed. This perspective is consistent with studies of time pressure, which show that people adjust effort expenditure in line with the rate of progress that's required to achieve the goal. And finally, there are theories that propose a non-monotonic relationship between difficulty and motivation, such that motivation is highest when the difficulty of achieving the goal is moderate and lower when the goal is either too easy or too hard. I've called this the achievability perspective because the inflection point is generally assumed to occur around the point at which the goal transitions from being hard but achievable to not achievable. Because of this potential non-monotonicity, we use a different function for the rate gradient, which via this alpha parameter captures all three of these possible scenarios. So putting it all together here, we've identified 6 theoretical perspectives that address how motivation might change as a function of distance to goal and time to deadline. And all these perspectives can be expressed as special cases of this more general 3 gradient structure. So our model just assumes that the motivational value of a goal M is just a weighted sum of these 3 gradients. So we can use this architecture to examine whether any one of these theories is sufficient to account for the dynamics of motivation in its own right, or whether more than one perspective needs to be integrated. We estimated the parameters of the model based on data from this farm simulation paradigm. In this task, participants had to grow crops to a target height by the end of each crop's growing season. In each quote-unquote day of the growing season, each time step of the task, they could choose between one of 2 treatments, which each increased the growth of one crop at the expense of the other. We manipulated the distance to the goal by varying the amount of growth needed to hit the target. We manipulated the time to the deadline by varying the time remaining in the growing season. And we also manipulated the goal type. So in some blocks, they pursued approach goals, which is what you see here, where they had to reach a growth target. In other blocks, they pursued avoidance goals. In these blocks, they had to manage weeds instead of crops. And the goal was to avoid reaching a certain height rather than to ensure that you reach a certain height. And the model assumes that the probability of prioritizing a goal was a logistic function of the difference between the motivational value of the goal and the motivational value of the other goal. And so the likelihood function is shown there on the bottom left. We estimated the parameters using hierarchical Bayes. Lots more information about this in the paper. To summarize though, the model fits were pretty good, especially given that this task is a little bit more complex than the other tasks you see in the decision-making literature. In order to compare the 6 perspectives I spoke about before, we used parameter estimates to reconstruct the 3 gradients for each participant. So we could see what that 2-dimensional plane actually looks like. So on the left is the predictions implied by each perspective again, and on the right is what we estimated for each type of goal. So for the approach goals, the first thing you should notice is that the estimated plane looks quite different from the gradient, the planes implied by each perspective. Turns out participants care about all 3 gradients when pursuing approach goals, and they do so in different ways. More on this in a minute. For the avoidance goals, the space looks most similar to the achievability perspective, and also somewhat consistent with the proximity perspective, suggesting that people cared about distance and the rate of progress, more so about distance and the rate of progress than they do about time in the avoidance context. You can also break these results down by participant, and by gradient in order to get a sense of what the individual differences look like. So in terms of the distance gradient, which is that top row here, most participants had negative gradients, so about 90%, and these negative gradients are shown in red. And this is evidence for the proximity perspective in favor of that discrepancy perspective. The time gradient was much stronger when pursuing the approach goals compared to avoidance goals, so people didn't care as much about deadlines in the avoidance context. And of course, that's consistent with what we saw in the previous slide, which was showed the aggregate. And finally, most participants had some amount of non-monotonicity in the gradient, at least according to how we define non-monotonicity, which was an alpha value of between 0.1 and 0.9. Although, as you can see, there was individual differences in where that inflection point stood. So this provides evidence for the achievability perspective in both the approach and avoidance context. What we can also do with this model is look at how gradients estimated from participants compare to what a normative model would do. So to look at this, we use dynamic programming to derive the decisions that would maximize the potential for goal achievement in this task. And then we fit the exact same model to those normative decisions. And that means we can compare the weights that people place on each gradient to the weight that the normative model would place on each gradient to get a sense of whether people are, say, underweighting or overweighting certain gradients. So here the bars in the graph represent the 95% credible interval on the difference between the weight estimated for participants and the weight estimated for the data generated by the normative model. There are some individual differences, as you'd expect, but the main takeaway is that in the approach context, people tended to overweight the distance and time gradients and underweight the rate gradient. In avoidance, they often overweighted the distance gradient, but they actually underweighted the time gradient, if anything. And the results for the rate gradient in avoidance were a little bit less consistent. They depended upon the experimental setup. So to wrap up, the main conclusion is that none of the 6 perspectives outlined at the start of the talk is sufficient to account for these motivational dynamics by itself. These dynamics are complex, and so we need theoretical integration and formalization to understand how they work. We found that all 3 gradients were relevant, though the time gradient appeared to only be as salient when pursuing approach goals, less so when pursuing avoidance goals. So to understand the dynamics of approach goal pursuit, we need to draw on at least 3 perspectives. We need the proximity perspective, we need the time perspective, and the achievability perspective. To understand avoidance, we need at least the proximity and the achievability perspectives. In terms of future work, what we're working on at the moment, and I was hoping to be able to include this in this talk, but unfortunately it's not quite ready, is using this model to predict substitutions in NBA basketball games. So a big naturalistic data set predicting when coaches decide to play their best players as a function of how far ahead or behind their team is and how much time is remaining in the game. We also want to be able to use this model as a front end for models of, say, speeded choice. So right now we're working on a follow-up project where we integrate this architecture with the LBA to explain how people regulate their response caution over a sequence of decisions as they're working towards a goal and as their time remaining to achieve that goal is winding down. Very happy to answer any questions or share more about those projects if people want to get in touch via email. So that's it for me. Thanks very much for taking an interest in this project. There's some references there. I've also put my contact details there. Feel free to get in touch. Any feedback is very welcome. And like I said, happy to share more details. You can also read more about the project, of course, in the preprint, which is there on the bottom right. All the best.